Right, question 1a, part 1. Clearly we're going to be using either Pythagoras' theorem or trigonometry, so I'm sure by this stage you've drawn for yourself the three SOHCAHTOA triangles that we're going to be using. You need to do that at the top of your exam paper. SOHCAHTOA. And you might want to have a go at writing Pythagoras' theorem as well, just in case. Right, so we're asked to find the length of side XW. X to W would be that side. I've got the hypotenuse. This is the opposite side, this is the adjacent. I've got A and H. This side's not in the problem, so we won't label it. Looking along my triangles, of course it's a cos problem, K, A over H. So for those of us that like using the triangles, the adjacent side is little x, the hypotenuse is 7, and in here we write cos of 42. One nice line of working, cos 42, cos 42, let's tidy that up. X is going to equal cos 42 times 7, there's a time sign in between those. I'm working that out on the calculator, 5.20201. There's more to come, and then we'll do some rounding. X equals 5.2, we're in centimetres, and that's been rounded to 1 decimal place. Right, the reason I kept that long decimal is because I'm looking ahead. I think we need to know that as well. Right, Frank wants to find the length of side AC, so that's the big long side. AC will be this one. It's not right angled, obviously, although someone has drawn a right angle inside the original triangle. Find the length of AC using your answer for the length of XW from part 1 above. Now if you look at XW above, you'll find that it's actually from this triangle here. This triangle here is the same as the triangle above, same measurements. So we've already done part of the work. We've already found this part from above. That was 5.202.013, and there's some more numbers along there. Right, so all that remains to be found is this piece. We've got a side length, which is helpful. We need an angle, however. Now we could find this angle using angles in a triangle. Lots of ways we could do it. I actually worked out this one here to be 48, which using subtraction made this one 62. But you could of course work out this one and have used this angle. So using this angle here, I've got the hypotenuse, and this would be the opposite side. So we're using a SOH problem. And for those of us that like the triangle, looking at the top of the page again, SOH, S-O-H. The opposite side is the one we're looking for. We've used a lot of letters. I might use Y for this one. This is the hypotenuse, and because I'm doing a SOH problem, I want the sine of 62. You might have done it a different way, as long as you show your working, get the right answer. So I know that Y is going to equal sine of 62 times 10. Y equals, and working that out, 8.82947. There's a few more digits there, we haven't finished the problem yet. So therefore the total length of side AC is going to equal the 5.202 added to the 8.8. We'll do some rounding as well if you look at your calculator, 14.03 centimetres, and I've rounded that to 2 decimal places. Right, so lots of ways to do it. You might have chosen a different way, as long as you get the right answer. Moving on to part B, and I think using a similar idea actually. reduce that a little bit more so we can get a bit more of the problem on. Right, show that angle GFH. So 3-letter naming system, there's G, F, H, so it's this angle in here we're talking about. I've got to show it's 42 degrees to the nearest degree. Right, I'm going to call it theta for an unknown angle, GFH. There's my right angle for this triangle. So using this side is opposite the angle. Here's my hypotenuse down here. Using this right angle points to the hypotenuse for the big triangle here, which makes this the adjacent side. So to find that angle, I'm going to use TOA. I've got the O and the A, so that would be TOA. Those of us that use the big triangle, TOA, T-O-A, the opposite side is 9, adjacent side is 10, and this is tan of theta. Right, so one line of working, or a couple of lines of working, tan theta equals 9 over 10, O over A. So theta is going to equal tan inverse. We're finding an angle. When you find an angle, you need inverse, which gives us a value of 42 degrees rounded to two significant figures, which is what we were supposed to show. Right. Now the next question, if I don't move the triangle, says to use trigonometry to show that Pythagoras' rule is true for triangle FGH. FGH. So this is for part 2. Now to show that a triangle is right angled, I'll just get rid of this and start again for part B. So you can imagine I'm answering part B now. To show it's right angled, we need to show that Pythagoras' theorem holds. And for this right angled triangle here, we'd need to show that 10 squared plus 9 squared is going to equal FH. This length along here is going to equal FH squared, and then Pythagoras' theorem works. So our first task, next task, is to find the length of FH. I think they've put these extra lines here to help us. We've got an angle, of course, we'll put the angle in. Right, so if I begin by finding this piece, here's my right angle for this triangle in here. I could highlight it and show you what I'm doing. For that triangle, I've got a hypotenuse. This would be the adjacent side, so I'm using K. Now I haven't got as much space here, so I'm just going to squeeze it in. So obviously we're looking for A. Hypotenuse is 10, and this would be cos of 42 degrees, right? So A equals cos 42 times 10, which is 7.4. I think there are some other decimal points in there. We haven't finished the problem, so we'll just keep a few more decimal places until we're finished. Right, so over to finding this side now. We're going to need another angle. So angles in a triangle, I've got 90, I've got 42, so we could find this one down here. And of course that's 48. So using this one I've got H, and once again this is another A. We've already used A. Perhaps I'll erase that. So I can call this one A now. Right, and we're using the smaller right angle triangle. So also erasing this so we don't get confused. in that question. So using this information here, the adjacent side we're looking for, the hypotenuse is 9 cos of 48. So we get A equals cos 48 times 9. Obviously you'd be writing this down below. And we get 6.02217. So adding the two A's, if you like, we can call them A1 and A2. Adding the two together, we get a total length of 13.45. A few more decimal places there. Right, so need some more space. You'll be writing down below. I'm ready to try Pythagoras' theorem. Obviously the left hand side, 100 plus 81 is 181. And if we have a look at FH, which is that total length there, the 13.45, and we try squaring that, perhaps with some rounding, would be 181 as well, to the nearest whole. And that will just be because of the rounding, or which number you use there. So we've shown that Pythagoras' theorem works, that this one squared plus this one squared equals that one squared, and you would perhaps need a sentence just to explain what you've just found. Right, now we're on to the last part of this question. There's a lot of space there for you working for the last part. Right, this one's going to get difficult as well. Proving Pythagoras' theorem for any right angle triangle. He starts with this diagram. First he uses the whole triangle. So let's highlight the whole triangle. That's the right angle triangle we're using, and there's the right angle up there. So this would be the hypotenuse down here. Right. I prefer to read this bit first and understand that. Cos of angle QPR. So QPR is this angle, and it tells me that the cosine of that angle if that's the angle we're talking about, the cosine equals PQ, which is this side, divided by PR. Cosine is K, which would be A over H. So let's just check what they're using. Here's my adjacent side, there's the opposite, and there's the hypotenuse. So what they've done is they've found the cosine of this equals A over H. Right, then he uses the smaller triangle PXQ. PXQ, that would be this one, to show that the cos of the same angle, so the cos of this one this time. Now using this triangle, you'll notice that the A and the H actually change, because using the smaller triangle, here's my right angle, so this becomes the hypotenuse, and if we're talking about cosine, this would be the adjacent side of the smaller triangle. So it equals PXA over the hypotenuse of that one. So yes, I agree with that. So if cos equals that and cos equals that, then of course we know that those two things must be exactly the same, because this right hand side is the same, so therefore the left hand sides are the same. So they've just written PQ over PR equals PX over PQ, which is what they've written there. And then I wonder what they've done to get the next line, PQ squared. Well, if you remember anything from algebra and solving equations, if you have one fraction equal another fraction, you can do a quick bit of cross multiplying. Only works, of course, in this situation. So PQ times PQ, and that has to equal side PX times side PR. This here we can write as PQ squared equals PX times PR. which is exactly what they've got there. So they've demonstrated that for us. And for part 1 it says, in a similar way, show that QR squared equals that. So without losing the triangle and moving away, we'll have a go at answering. So this is now answering part 1. And for part 1, just to keep referring to it, we want to show that QR squared equals RX times PR. Right, so we need an angle, PRQ. So we'll start with this one, which is angle PRQ. And we'll write down that the cos of PRQ, A over H, and we'll use the big triangle first. So we're using the big triangle. So for the big triangle, the hypotenuse is this side. Let's get rid of those, which is side PR. And the adjacent side for the big triangle would be this one down here, QR. Right, and now using the small triangle, once again A over H, this is for the small triangle this time. Right, in the small triangle the right angle is here. Here's my angle, PRQ. So the hypotenuse for the small one would be this side, QR. And for the small triangle, the adjacent side would be this one, which is XR. Right, so if cos PRQ equals that, and cos PRQ equals that, then those two things must equal each other. And similarly to what we did before, if you have one fraction equaling another fraction, and only if you have this situation with the equal sign in between, you can cross multiply. So I'll get QR, and QR times QR is going to be QR squared, and that's going to equal XR times PR. Now I hope that's what we were looking for, so just check up there. Yes, so we've done it. Right, part 2 says use the results above to prove Pythagoras' rule for triangle PQR. So that's the big one. So we need to show that that side squared plus that one squared equals the big long one. So we just get rid of some of that. We'll go back and highlight the whole thing again. Rid of that bit. Oops. Pythagoras' theorem. So QP squared, or we'll call it PQ squared, plus, and now we want QR squared. I'm hopefully going to show it equals all of that squared. So using the information we've got already, I can see that PQ squared is PX times PR. PX times PR, we're using the dot for times, plus QR squared is RX times PR. RX times PR. Well, we haven't really got very far yet, except that I notice that both terms have a PR in them. So we'll do some factorising. Common factor of the PR, we can pull that out in front. So this equals PR. Now I have to times it by a PX plus an RX. PX plus RX. Of course, another way of writing PX plus XR is PR. When you add those two sides together, you'll get another PR. And of course, a shorter way of writing that is PR all squared. So you'll obviously have more space down below, So I've just proved Pythagoras' theorem that that side squared plus that one squared equals the long side squared. You might like to write a sentence underneath, hence Pythagoras' theorem works for triangle QPR.